Welcome to the Explainer. So, today we're unpacking a concept that is basically the ultimate safety net for artificial intelligence and machine learning. It's called cross-validation. If you've ever wondered how data scientists know for sure that their AI won't just completely fall flat when it finally faces the real world, well, this is their secret weapon. We're going to dive into exactly how this works, why it's absolutely crucial, and uncover a pretty surprising twist about how models are actually put into production. Here's our roadmap for today. First up, the data split dilemma. Then, what is cross-validation? After that, how K-fold works. And finally, number 4, the final model twist. Oh, right. Let's dive right into section 1, the data split dilemma, or the problem with using all your data.
Okay, so the golden rule of training any AI model is that you absolutely have to test how well it predicts data it hasn't seen yet. Makes sense, right? But if you use 100% of your data to teach the model, you've got literally 0 left over to test it with. And if data's tight, that's a massive problem. So the classic go-to fix is the 80-20 split. You chop up your data set, giving 80% to the model so it can learn the patterns, and locking that remaining 20% away in a vault. It stays completely hidden, ready to be used as a test later. Sounds pretty logical, doesn't it? But here's where we run into a major roadblock. What if that 20% you saved for testing is, I don't know, particularly easy, or maybe incredibly hard? A random, simple split is basically just a gamble. The 20% you happen to pick might have a bunch of data points that make your model look like an absolute genius. Or, on the flip side, data points so weirdly difficult that it makes the model look terrible. Either way, you're not getting a true, accurate read on the model's actual predictive abilities. Now sure, random sampling helps a little bit, but we really need something way more robust than a coin toss. Which brings us to section 2. What is cross-validation? Basically, the hero of data sampling. So while that random sampling does help with the 80-20 dilemma, what we really want is to use absolutely all of our data for testing, without completely ruining the training process. Enter our hero, cross-validation. This is the process of partitioning a dataset into multiple subsets and training the model multiple times. Essentially, each time you do this, a different subset steps up to act as the validation set, while all the rest serve as the training sets. To put it in plain English, we break the data into smaller pieces, and those pieces take turns. One gets to be the test, while the others are the study material. This gives us a wildly better estimate of how the model is actually going to perform on unseen data. Moving right along to section 3, how K-fold works. Rotating the data. So K-fold, that's really just the technical term for this rotating method we just talked about. The K literally just stands for the number of chunks we slice our data into. Let's think back to our classic split for a second, an 80% training slice and a 20% testing slice. But now, instead of just slicing it once, crossing our fingers, and hoping the test set isn't weirdly skewed, we are going to systematically manipulate that split. Let's walk through exactly how a 5-fold process works. It's actually super clever. Step 1, we divide our data into 5 equal chunks. Step 2, we train the model on 4 of those chunks, so there's our 80%. Step 3, we test on that one remaining chunk, our 20%. But here is where the absolute magic happens in step 4. We repeat this entire process 5 whole times, shifting that test chunk every single time. So chunk 1 gets a turn as the test set, then chunk 2, then chunk 3, and so on. The final result, that's step 5. We guarantee that every single data point ends up in that 20% test set exactly once. By the end of it, we've used literally every data point we have to truly understand how well our model predicts new data. It's brilliant. And that brings us to section 4, the final model twist, the surprising truth about production models. Okay, slow down for a second, because everything we've talked about so far leads to a really, really common misconception. You might reasonably think, okay, after running those 5 different training sessions, I'll just pick the best one out of the bunch and deploy it, right? Nope, we absolutely don't do that. Here's the twist. Cross-validation is for model checking, not model building. We actually don't use a single one of those 5 trained instances for our real-world predictions. The whole purpose of cross-validation isn't to build your final model at all. Think of cross-validation more like a testing arena. Say we've got 2 completely different models, like a linear regression model squaring off against a neural network. How can we say for sure which one is better for our specific problem? Well, we run K-fold cross-validation on both of them. It's basically a competition to see which architecture does a better job at predicting those rotating test chunks. Cross-validation, it just helps us pick the winner of the fight.
So, what actually happens after we crown our winner? Let's say the neural network crushed it and proved to be the better model during validation. For our actual final predictive model, the one we're going to ship out into the real world, the magic number is 100. We want this model to be the smartest, most experienced version of itself possible. So we train that winning architecture on 100% of the data we have, every last drop. We don't use those practice models we trained during validation. The testing phase is completely over. The checking is done, and now we build the final model with everything we've got.
So, just to summarize that actual production pipeline, cross-validation picks the winning model, and then the final model is trained on all the data. But hey, it's machine learning, so of course there are exceptions to the rule. There's an advanced technique called bootstrap aggregation, usually just called bagging, and it actually does use those model instances produced during a similar validation process to build up what's called an ensemble model. It's a super fascinating exception that kind of bends the rules we literally just established. Which leaves us with a pretty provocative thought to wrap up our explainer today. If techniques like bagging can just break the standard rules of model building, what other AI secrets are hiding out there in ensemble methods? The whole world of machine learning is absolutely full of these incredible structural twists. So keep questioning how these systems are truly built, keep learning, and I will catch you in the next explainer.